a quick note before we start here. Nothing in these notes is introducing a new geometry concept. These are all things that you have seen before. The goal of what we are doing here is to refine a particular skill, and that skill is your explanations and being able to explain the reasoning and thought process behind the statements that you make and being able to back up what you know is true with being able to say why it is true. So we're going to do some examples with that today. I want to encourage you with each example to pause and try it yourself before seeing how I do it and seeing how those compare. Let's get started. We're going to start with B is between A and C. And for each of these, we're going to say what we know is true about this diagram and why we know it has to be true. So let's start. Since B is between A and C, that means that I have A to B here, and I have B to C here. Then I also have the entire segment from A to C. And what we have learned is that those pieces add together to get the whole thing. So that's the statement. That's what we can conclude, is that I can add up the pieces to get the whole. And then we're going to explain why that is true. So my pieces here are A to B and B to C. And then my entire length is A to C. And again, this isn't anything new. This is one of the first things we learned this year about geometry, is that these two pieces of the segment add to get the whole thing. But what we are going to work on is being able to explain how we know this. And there are two different approaches. I'm going to show them both in this first example. There is a shorthand name for this that we learned. So you can memorize the shorthand name for this that we learned, or you can just explain what that thing says. So the explanation first. So that involves literally writing out the sentence that is true. Writing this out as a sentence as to why this works. So I'm going to say A to B and B to C are pieces of the segment so they must make up the whole thing, which is A to C, when combined together. And if you want the shorthand name for that we called it the segment addition postulate. But if you're saying that, you need to say that exact wording, segment addition postulate. And that is just the shorthand way of expressing this entire sentence, which is basically saying that the pieces should add together to make the whole thing. So what we are explaining is, okay, why does A to C go on the right side? And why do A to B and B to C go on the left side? And why are we adding? So we are explicitly stating out why we are doing those things and why we are allowed to do those things. So that's the skill that we are kind of developing. And again, before I do number 2, which I'm about to do, I encourage you to pause. I'll give you a hint first, which is that A to B bisects C to D. So what that means is that C to D is the one that's being bisected. C to D is the one that we care about. So that is the one that is actually bisected. So think about what bisected means. If you need a further hint, here's the tick markings we would put in the diagram. So based on that, what do we know is true about that segment, C to D? What is happening to it? And how do we know that's what's happening to it? I'll give you a moment if you want to pause and try it. Okay, the statement that we know is true here is that C to E and E to D are congruent. In other words, these pieces are the same. And our reasoning for that, we're basically going to explain bisectors. The shorthand way, if you want to memorize the exact phrasing, is definition of segment bisector. But I'm just going to explain what the definition of a bisector is. Since C to D is being bisected, it must be split, and we're going to say where it's being split exactly, which is at point E into to equal, which is why we're making them congruent, to equal pieces. So since C to D is being bisected, it must be split at point E into two equal pieces, which are C to E and E to D. So we're explaining what a bisector is and what it does. That's number 2. I'm going to go down to number 3, but before I do, again, I'm going to give a moment to pause and for you to think about what can we say about this last diagram. More specifically, I'll give you a hint that we're going to say something about the angles here. All right, welcome back. And when I did this in class, I noticed that most people were able to say the thing that is true, which is that they're supplementary because they're a linear pair. But we're going to be more detailed in 2 ways. First off, when we say they're supplementary, we're going to be specific. What are we saying are supplementary? Just like in this one up here, we said which pieces specifically had to be congruent. It's not just they're congruent because of a bisector. We're saying C to E and E to D specifically are congruent. So up here, we're going to say which angles specifically are supplementary, and we should be naming 2 angles. So we're looking at BCA, and we're looking at angle ACD. And we're going to say that those measurements add up, since they're supplementary, to 180. So they add to 180. And I'm going to explain why. These 2 angles are a linear pair. Now, I'm going to say more than linear pair, because if I just say linear pair, then I haven't connected linear pair to supplementary, right? I'm not convinced yet that just because they are a linear pair, they're called a linear pair. How do I know that they make 180? So I'm going to elaborate and make that connection. These two angles are a linear pair. Therefore, they combine to form a straight line. Which must measure, guess what it's going to measure? It's going to measure 180 degrees. And now we have connected, linear pair means straight line, and they're combining to make a straight line, and a straight line means 180, so that's how we know they're supplementary. So now we have said more specifically a proof and shown why the term linear pair, what that has to do with adding to 180. And again, if you want the shorthand way of writing it, if you want to just memorize a phrase instead of having to write out this whole sentence, it is linear pair postulate. I like the sentence better because instead of having to memorize some magic phrase, you are actually just writing out, here's why this is true. It's a more plain English way, which I think might help some of you in understanding how these explanations are created. So, where this is headed and why we're working on our explanations is that we are going to work next time on something called a proof. So let me just introduce that very quickly before we go here. A proof is an argument for a mathematical statement. So this is a proof showing that certain assumptions must logically lead to a particular conclusion. So what a proof is going to look like is it is going to follow step by step and say, if I start with knowing this thing, I can step by step make an argument of saying that means that this has to be true, which leads me to this conclusion, and I can bring in this other piece of information to combine with it to say, therefore, this final conclusion has to be true. And when we make a proof, the structure in each of those steps that we create should have two pieces to it. We should have a statement telling what you are saying is true, and a reason that justifies why that thing must be true. So basically, up in those previous examples, we were laying out what one of these statements and sentences might look like. And so, when we go down here, these reasons can be explanations and properties and definitions, all the things that we have talked about. But each step must have a reason justifying why it is true. In other words, if you are saying something, if you catch yourself saying something like, oh, this means that these measures are congruent, or that means this thing has to be this measurement. Well, you need to back that up. You need to back that up and explain why you think that is true. So, I want to leave you with something to try here, which is this first example. What we're going to do is we're going to prove the vertical angles theorem. So, using the diagram on the right, prove that angles 1 and 3 must be congruent. So, I'm going to prove these two angles have to be congruent. And I want you to try that before you come back next time. I want you to try that without using vertical angles. So, you are not allowed to say those two angles are vertical angles. They're across from each other. They have to be the same. right? I want you to make that argument without, pretend I never told you the vertical angles were congruent. Pretend I never said anything about what had to be true about these angles 1 and 3 across from each other. And think about how we could still get to the conclusion if I knew angle 1, how I could get to the conclusion that angle 3 would have to be the same as angle 1. And so if you're getting stuck with that, my hint is to maybe try out some measurements. So see if you can think about, pick a number for angle 1, like 50 degrees, say angle 1 is 50 degrees, and see if you can use some of the other angles in this diagram to get to a conclusion of that angle 3 would also have to be 50 degrees. And then see if you can generalize that argument without those specific numbers, that specific measurement of 50 degrees, to say, this is what in general is always going to happen that will cause angle 3 to match with angle 1. So try that, and next time we'll come back and I will show together how that works.